Okay, hello everyone. Sorry for keeping you from your lunch. I'm Sachin Kamboj. I'm a software engineer at Bloomberg, and I'm going to talk about GitOps and OperatorOps. So first of all, by a show of hands, how many of you have heard of GitOps? Okay, just about everyone. Thank you. How many of you have heard of OperatorOps? Okay, that's good. It's not completely new. Okay, how many of you love GitOps? Wow, just one or two. I wasn't expecting that. How many of you hate OperatorOps? Oh, GitOps, sorry. Okay. Okay, more or less. So I made this slide thinking that everybody loves GitOps. Perhaps not, but the question is, why do SREs or DevOps people love GitOps? So the first reason is the idea of infrastructure as code. You have some declarative configuration. In this case, or this example, I have a Kubernetes cluster. I say I'm running version 1.31.4, and I have 200 worker nodes, a monitor pool. And the idea is I store this configuration in a source of truth. You want a single source of truth for this. You have a magic CI/CD pipeline or workflow, and boom, some minutes later, 5 minutes, 10 minutes later, you get a 200 node fully provisioned cluster ready to go. Why is this a powerful concept? One of the big reasons it's a powerful concept is it allows us to treat our infrastructure as cattle, not pets. So the idea is, oops, my cluster is misbehaving, delete the cluster, completely rebuild it from scratch. Everything works great. If I need to, like, say, move to a different region or need to provision a different cluster, I can copy paste the configuration, make a few edits here and there, deploy it, boom, I have a completely brand new cluster. So that's an awesome concept, no doubt. The other big reason is change tracking. Anytime I want to make a change, I just have standard Git. I can look at what the diff was. I can see what was the change that was made, which is super powerful. And it gives us nice things like reviews, approvals, and auditing. So for example, if I look at something's broken and I was like, hey, who was the idiot that pushed this out? And I want to go and shout at that, I can go in GitHub and look at it. And in 99% of the cases, it's usually me who was the idiot who pushed it out. So I only blame myself. But it gives you this idea behind that. And the whole idea behind there's somebody who's approving a PR. You do not merge or you do not deploy something until it's approved, and you have auditing in place. And then another big example, rollbacks are simple. Let's say I decided that what I wanted to do was I wanted to go from 200 nodes to 150 nodes. I did a PR that reduced the number of nodes in the worker pool to 150. I figure out, oops, that's not sufficient. I have pods and pending states, or some things are not working and I want to go back. I can just do a commit and say revert, and boom, I'm doing. So everything is perfect. GitOps is the future. That's the end of my talk. Let's go. We're done. Except that it isn't. GitOps works great when there is a single cluster. What happens when there is multiple clusters? So in this example, I have something like 10 clusters shown here. By a show of hands, how many of you have had to manage several hundreds of clusters? At least a couple of us. You know the pain behind that. And there are people who have had multiple ways of dealing with this. Usually the two extremes is apply an individual PR for every single cluster. And you basically get PR fatigue, unless you have mindless intern that's going to be magically going in and changing every single cluster's version from 131.4 to 132 something. It's really not going to work. And moreover, whoever is approving those PRs is probably going to blindly be approving those PRs because they've done so many of them that they're not even going to look at the change. So I would argue it's no better than ClickOps. The other way, which is what I call the YOLO way, is let's just find all the instances of 131.4 and replace them by 132.2, and boom, we're done. All the clusters have been upgraded. The only problem with that is that blast radius can be huge. We only live once. And then the usual way in which people do this is they have some kind of workflow that they put on top of it. And the idea is they'll try to apply stages, batch up updates and apply them in stages. But anyways, that does not quite always fit the GitOps model, because the idea is you have an automated tool that's now making PRs for you. And the whole idea behind having auditing and having approvals is you would see like the person who made the change. Now it's the GitOps tool or the automated workflow tool that's making the change. So, okay, the other big problem is that complexity is often hidden in the pipeline. So to discuss this, I'm going to actually cover a concrete example of a bug that we faced that caused a huge amount of issues for us. It caused an outage. So this is the bug. I'm going to walk you through it. So a lot of bullet points. This is just an indication. This bug actually caused a real outage on multiple production clusters. One thing I'd like to say before I begin, there wasn't really a root cause, because one of the things they point out is there's a root cause. No, there were multiple factors that contributed to it. And I don't want to blame one person or a junior developer did this. I did not actually cause this, but could have been. Okay, I could have been responsible. But anyways, one of our teams migrated from old mechanism of creating namespaces to using the Terraform provider Helm, which is where this bug lies. So this was a SRE. They were on call. They had nothing to do on that wonderful day. So they decided, you know what, I'm going to do some automation. Right now, we create namespaces more or less by hand. What I'm going to do is I'm going to automate the creation process. Perfect. Standard thing. You should do that. Now, unfortunately, when we applied this change, it actually deletes all the namespaces before recreating them. This is the bug in the code. So ideally, what you should do is if a namespace already exists, there's no reason to delete it and recreate it. You should just move on or try to reconcile that. This didn't do that. The Terraform provider actually went in and, hey, your namespace, I don't like you. I did not create you. Go away and I'll recreate you. Okay. What's the problem with that? The problem in Kubernetes is, if you know anything, if you delete a namespace in Kubernetes, it deletes all the resources in the given namespace. And as a result of this, it deleted some secrets. And here's the kicker. The secrets only existed in the namespace. There was no other source of those secrets. That's what's the problem. So going back to infrastructure as code, the secrets should be in code. We should be able to recreate them. No, the secrets only existed in the namespace. You deleted them. They were lost forever. Okay, who was the idiot? Didn't they check this or test this out in staging? Of course they tested it out in staging. They did not hit that bug because the staging namespaces did not really have any existing resources. Wonderful. And this change was considered really low risk because it's not like it's creating namespaces, it's not deleting things. All it's supposed to do is automate the creation process. So it was considered low risk and it was rolled out to all clusters in prod at once. And all resources except secrets could be recreated from GitOps. That was the only part that couldn't be recreated. I'll go into secrets and GitOps in a later slide. But the big problem was secrets had to be recovered from etcd backups, which was painful and time consuming. Another fun fact about this incident, I actually got called on my birthday. So anyways, this is what I mean by complexity is hidden in the pipeline. There's a lot of magic that happens. And unfortunately, I'd like to say I have a good solution for this, but I really don't. We need a lot of magic for any kind of automation that we do. Okay, next problem. A status of the rollout is not really visible in Git. So if we look at this PR, it says, I updated the cluster to 132. It also updates the base image. I deployed it, it merged, perfect. Except that the application of the state is usually asynchronous. Git shows the desired state. It does not really show the actual state. That actual state is elsewhere. At best, what it can do is it can show that your pipeline succeeded, or it can show a check mark saying that you did something, but what is the real state? And also, was it applied completely? Was it applied partially? Did the whole thing work? Did some of it work? I don't know. It doesn't really show much in the Git operation. And furthermore, there's really no reconciliation of failures. Let's say you were talking to an external service. The service was down for whatever time. You probably have something in your pipeline where you try 2 or 3 times with an exponential backoff and jitter. You give up and you're like, okay, this thing failed. The service comes back online in 5 minutes or something like that. It's not going to run your workflow again. Finally, the one big problem with GitOps is managing secrets is a royal pain in the neck. What do I mean by that? The first thing people tell you is do not commit secrets to Git. Absolutely do not. What solution do people do? They decide, okay, we're going to encrypt the secrets and store it in Git. So you end up with something like this. Can anybody look at it and say whether the access key and the secret key is right or wrong? Nope. So how do you even review PRs with somebody changing a key? But the biggest problem with even this, and there are multiple solutions that do this kind of encryption, how quickly can the encryption key be rotated? Let's say somebody leaves the company, or if it's an asymmetric encryption key, or it gets leaked or something else happens. If what you have to do is go through every single line of code and find the encrypted secrets and decrypt them and re-encrypt them, you're asking for a lot of pain. So finally, rollbacks can be complicated. So in theory, I said you can just revert a commit. Perfect, should work. Except in this case, I'm reverting update Captain Kirk cluster to 132. I decided to update to 132, found an issue with the cluster. I want to downgrade, except that Kubernetes does not support downgrades. So I can't really do this revert. Another example of this, how do you do rollbacks of things like database schema changes and stateful sets? So while researching this talk, I came across another really good blog post and a talk that talks about GitOps and database rollback, and their approach is similar to what I'm talking about here. But the whole idea is if you have a database migration, typically the way people do it is they define a database migration up script and a database migration down script, except nobody really defines a database migration down script because it's almost impossible to do it in a nice, safe way. So I would recommend people do that talk. And then the final problem with GitOps is that it really does not handle day two operations very well. So what do I mean by day two operations? Things like I need to defragment a member, I need to compact a member. These are very common things you would do on an etcd cluster. I perhaps need to reset a member, it's behaving, the disk is bad, whatever, I have to take it out of service. The membership changes, I need to back up and restore things. There really isn't a good way of doing this in GitOps. So enter OperatorOps. So what is OperatorOps? So let me walk you through them a little bit. By a show of hand, how many people are familiar with Kubernetes operators? Quite a few of them. For those of you that are not familiar with Kubernetes, so Kubernetes operators are built up of two key parts. There's the CRD, or custom resource definition. The idea behind the CRD is back to my original example of declarative configuration. The declarative configuration is the CRD. It defines a very well-defined schema to your declarative configuration, and it has, the next thing it has is a controller manager. So the controller manager has this idea of constant reconciliation. It has the controller loop. The idea behind it is there's a desired state. The desired state is what is that YAML or JSON or SCL that you represented. There's the real world, and it's observing the actual state. So it can do a diff and figure out what's the difference between the desired state and the actual state. And it can act on the real world to try to make the actual state equal to the desired state. So this is a constant reconciliation loop. It's always looking at the desired state of something. It's trying to make it equal to the actual loop. The final piece of the puzzle that you really need in order to make all of this work is the Kube API server, without which nothing really works. There's one part that I left out, which is also the database or the single source of truth. That's typically goes with etcd. You can use Kine and Postgres and other backing stores for it. But the whole thing that the Kube API server gives you out of the box is it gives you auth-in and auth-c. It gives you a RESTful API. It gives you schema validation, auditing, watches, multi-version concurrency control, and a whole bunch of other things that you get out of the box just by having a Kubernetes API server. Okay, I described operators. I haven't really described OperatorOps and what are OperatorOps. But before I describe OperatorOps, I want to give a concrete example. And the example that I want to give to you is of a completely made-up service, or might not be a made-up service, of etcd as a service. So what is etcd as a service? And in this example, what does it look like? So etcd is the backing store for Kubernetes. If people are familiar with, let's say, Zookeeper or one of the previous ones, or a lot of people know etcd, all your data in Kubernetes gets stored in etcd. And an etcd's cluster is typically made up of an odd number of nodes. So in this example, I have 3 examples here. I'm calling them cohort, will be clear why. But we have either a 5-node etcd cluster or a 3-node etcd cluster. The biggest problem with this model is that each node itself is pretty hefty. So we're talking about something like 56 cores, more than 550 gigabytes of RAM, 3 terabytes of hard drive space. If you know about anything about etcd, the default maximum size of an etcd database is 2 gigs. I've seen clusters that people provision etcd with 8 gigs or 16 gigs, but 2 gigs is the default. That means the entire etcd database can probably fit in memory. You probably need less than 4 gigs of memory. You probably need no more than 1 or 2 cores, and you need very little disk space. So if what you did was hosted 5 bare metal etcd nodes just to maintain etcd, you're wasting a huge amount of resources just for having an etcd instance. So our solution for etcd as a service is we run multiple instances of etcd on a given node. So if you look over here, what we do is we run multiple instances of etcd. They're spread out across 5 nodes because we need replication, we need quorum. And we call each slot an SREday instance. Each instance is completely independent from another SREday instance. It's a full SREday cluster. It just listens on a different port, and that's about it. So back to SREday as a service, the key idea is there are cohorts. Cohorts are made up of nodes. There can be 5 nodes, there can be 3 nodes, there can be even 9 nodes if you're doing a stretched SREday for something wacky. And then the nodes are subdivided up into instances. And nodes and instances together make members. So what are members? If you look at every single one of these boxes, it's actually a process running on a given node. And a process running on a given node that forms a part of an SREday cluster, an SREday instance, is just called a member. That's our terminology for it. Okay, so how do we get SREday as a service? The biggest way we do it is, again, back to infrastructure as code or declaration. We have a CRD or a CR. We specify, I want an SREday with the version. I want these set of nodes. I want X slot. I apply that to some magic pipeline or an operator, and I get back a status. And in this example, we can see we have a cohort, which let's say it reconciled successfully. It consists of 3 nodes. The nodes is made up of 7 instances, and 7 instances are made up of a whole bunch of members. Okay. So the nice thing about OperatorOps is we can use this for day 2 ops. So there are a whole bunch of ops that we can do using these resources, which are called cohort ops, node ops, instant ops, and member ops. And this is an example of things that we can do. So let's say we want to upgrade the whole cluster. So typically, if we this was a production service and we had SREday running on 5 nodes, we probably have somewhere from 32 to 40 instances of SREday running on a node, and we don't want to YOLO it. We would probably create something like an CRD that says, hey, I want to upgrade to 3.5.17. I'm upgrading from 3.5.9. I want to batch it in 2 clusters at a time, and it's like an upgrade version. Or I can do something like I need to remove a node because that node has gone bad and I need to take it out of the service and replace it. I can do something like that. Or there can be very simple operations like instance or instance ops where I'm operating on a single instance and I want to compact that instance or defragment that instance. So let's see if I can actually do a live demo of this. It's a live demo, but it's running entirely on my laptop, and hopefully the demo gods are good. So let's see. Oops. So do that and try that. Okay. Can you still hear me? Let's see. Give me 2 seconds to get set up. Where's my cursor? Okay. Let's just clear. Okay. There's no way you can see that. Let me get rid of some of the noise. Okay. Okay. So the thing that I just showed, if I do cohorts, that's the cohort I was talking about. I can do nodes. Those are my nodes. They're not namespaced, so I can do all the nodes. I can look at instances. Those are all the instances. And I can look at members. Okay. So in the example that I wanted to show you, let's try to do something very simple, which is I want to compact an instance. So compaction is the idea. If you know anything about SREday, it basically keeps every version of every operation that you're performing against the database in a log. And compaction is just saying, get rid of the old history because I can't let my database go forever. So if I looked at this, hopefully, can you see this? Can I make it better? Okay. So this is what it looked like. I just have the instance name specified. So SREday demo 1, and I want to run it. So just to show you before I run this, I can do a kubectl get instance ops, and I'll do a watch. And then I'm going to apply this. No, this is the compact instance. Okay. So that's all I really had to do. I applied the compact instance. It went in. It said, starting reconciliation, instance op completed. My database got compacted. The one thing I can do is if I do get instance ops, what's the name? Wait, what was the name? Oh, yeah, let's do -n. No, this is compact. Okay. If I look over here, one of the things that this tells us is inside the conditions, it has a bunch of conditions. So before doing any operation, it first checks whether all the endpoints are healthy. And then after checking the endpoints are healthy, it actually does the reconciliation. So it's giving me status on everything that it's trying to do. Okay. So an instance compaction is very Simple because it's one operation that's done on the whole instance, which means you just connect to the instance and give a compaction command. There's nothing fancy about that. It just makes day 2 operations really simple. Let's see if we can do something a little more fancier, which is defragment. So the way defragmentation works is you want to really go in and defragment every single member of your cluster. But the way we're going to do it is we're going to do it member by member instead of defragmenting the entire cluster all at once. So before I apply this, or actually, no, I can just apply it. So if I do an apply -f defragment instance, if you look at what it's doing, it basically, again, started reconciling and did a bunch of things to make it true. But what it really did in the instance ops is it actually created member ops. Can't spell, sorry. It created member ops, and that's what it's basically reconciled, which is it created a bunch of member ops, and then it reconciled each member individually. So let's see if I can see some conditions about this. Get member ops -n. Let's do that. -o YAML. This one doesn't have a condition. Sorry. Okay. So that's defragment. Okay. Who the hell cares? Nothing much about it. Let's see if we can do even something crazier than that. So ideally, I would have a bunch of watches. If the screen was bigger, I would show you both the cohort ops, member ops, version ops, and things like that. I'll just do a watch with the cohort ops. Let's do that. And the next operation that I'm going to see is cohort. No, I want to see the upgrade operation. Okay, so remember I showed this? I have a whole bunch of instances. They're all on version 3.59, 4.9. So if you do get instances -a, you can see all the version is 3.5.9. What I'm going to actually do is I'm going to apply this cohort op that is going to try to upgrade them to 3.5.17. And while I do that, I can do a get node ops. So if I look at node ops, it's basically telling me I successfully downloaded the etcd version. If I looked at the instance ops, what it's doing is it's basically the batch size I specified as 2, so it's only going to do 2 instances at a time. The current batch is the batch that it's working on. It's basically going to upgrade each version, so it's going to do it one at a time. And if I look at the member ops for this, it actually operates on 1 member at a time for each instance, which is the safest way to do an update of, member ops. Oh, come on. I can't get the spelling right. Member ops. Okay. So it's basically going through a version at a time. And once it does all the upgrades, it says all instances processed. And I can see that in my instance ops, all of them completed. And if I look at my instances, I can see, oh, look, they're all working at 3.5.17. So that's an example of an upgrade. The final example that I'm going to show you today is what happens if I want to remove a member. Oh, before I apply it, this is the member itself. So let's say I want to get rid of this entire node because this node is bad. It's misbehaving. It doesn't work. What I can do is I can kubectl apply this. Okay. And again, it's going to go batch by batch. It's going to remove that member from all the instances. And then it says all instances done. If I do kubectl get nodes, wrong kind of nodes, that node doesn't exist anymore. If I do members, those members don't exist anymore. So this is a way of safely doing some operations. I understand that I'm the last thing standing between you and lunch, so I won't actually do a demo of completely deleting this etcd cluster and recreating it from scratch, but I also have that as a demo that I might be able to do. Sorry? Okay, who wants the demo of deleting? Oh, I was not expecting that. Okay, let's do that. So what I'm going to do is I'm going to actually delete. This is a made-up example because it's running on my laptop and it's not using any of the wonderful infrastructure things. But I'm going to entirely delete that cluster, the kind cluster, and I'm going to actually reset all my nodes. So it's running 3 parallel nodes for a 3-node etcd cluster. And let's see if I can create the cluster. Okay, let's try starting from scratch and let's hope this works. Okay, so the first thing I want to show you is what I'm going to do because I just don't want to be running commands. from scratch. So what am I going to do? The first thing I'm going to do is I'm going to start a kind cluster. So this is an example of creating a Kubernetes cluster. I'm going to install Cert Manager because we use Cert Manager for all the certificates that we need for etcd and to handle rotation and things like that. There's something known as Carlos. Ignore it completely. It just does allocation. Not just needed because whatever. There's a component called Carlos. You don't care about that. It's going to run it in the cluster. The other thing it's going to do is it's actually going to exec into the node, and it's actually going to copy the CAcert for the kind cluster. The reason it's doing that is because I need every single node to connect to that kind cluster. So I need to do that. And then it's going to install a secret. It's going to basically install the CRD. So let's do this first. So it's new SRT node. So now I'm creating a brand new kind cluster. This is going to be my source of truth. This is going to be the management cluster that runs the entire etcd. Okay, let's see if it works. Give it a minute. So it's loading Cert Manager on there, or actually it's loading the images because I designed this to work if I had no internet connection. I'd applied the secrets. Let's see if this works. Okay, this step always fails for some reason, but no matter. I'm going to apply it manually. Okay, that was the step that failed. And then I'm going to install a bunch of CRDs. Okay, CRD is installed. I'm running the operator locally. So this is running the operator. Perfect. Okay, next thing I'm going to do is, this is where, oops, sorry, there's an annoying box on my screen, which is overlapping what I'm actually looking at. Okay, so that's the cohort that I'm going to try to create. It consists of 3 nodes. These 3 nodes are just going to run in parallel with 3.5.9. So I'm going to do, and there is one manual step that I have to do just because I don't have wonderful automation running on my laptop, which is once I apply this cohort, I'm actually going to run this script, which is going to create a kubeconfig. So every node gets its own specific kubeconfig. The idea behind that is we never want to share secrets and never want to share certificates. We need to copy those kubeconfig and the binary to the node. So that's what these scripts do. Okay, so what I'm going to do is I'm going to, and before I do this, let's actually set up some watches. So I'm going to get cohorts -a minus, oops, I don't need -a. That's not a namespace thing. And let's do a kubectl get instances -a minus w, kubectl get nodes -a minus w. Actually, that's not namespaced either. And kubectl get members. Okay, so right now they're not returning anything. It's just a watch. And the reason for that is we can watch it do things. So what I'm going to do now is I'm going to apply this cohort. Okay, and I am also going to copy over this things to, oops, to all the nodes. Okay, and meanwhile, things are happening over here. First thing that's happening, the cohorts, it says, oh, let me make this bigger. Cohort reconciled successfully. This doesn't really do much, this operator, so this is not really interesting. This is the interesting part. It says node reconciles successfully. What it really does behind the scenes on this node is it actually downloads and installs a lot of binaries and all the things that it needs to set this up on each node. If you look at the conditions, they tell you information about it, but the conditions typically have negative polarity, which means the conditions only become true if there's something that fails, and it will tell you why it failed. So mostly, oh, good. No, yeah, so the condition really doesn't say much over here. If I look at what's happening, oops, over the instances, it's actually trying to start up those instances. So 3 of them have already started. The other 2 are still working, and I can do a kubectl get members, and it's trying to create those members. And boom, at the end of it, I have a fully functional etcd cluster recreated from scratch just by using operators. Okay, that's the end of my demo. I could probably do the operations on them again, but you know, why? Let's see you. Okay, so finally, this is a end of summary of what I want to say. So do we want to use GitOps or OperatorOps? So both GitOps and OperatorOps give us declarative infrastructure as code. They give us a single source of truth, which is awesome. There are still 2 things that GitOps does that OperatorOps does not really do that well. And one of them is change tracking. And the second thing is reviews and approvals. Although we do have a way of doing reviews and approvals using OperatorOps, but that's a very technical, deep kind of thing that I won't get into how we achieve that. But change tracking or just being able to see and get that you made this change is incredible. And we don't have a good solution for that in OperatorOps. Auditing, Kubernetes comes with a lot of built-in auditing that is super awesome. But being able to see something in a GitHub commit or GitHub PR is really nice. But I would say one of the things that OperatorOps really shines at is the idea behind doing multiple clusters, behind doing rollbacks, reconciliation, secrets. The way secrets are handled is typically Kubernetes secrets. You can actually integrate with vaults and use Vault as a service or other ways of handling secrets. But the biggest thing that you can do with it is day two ops, which is the idea that was presented in this. Okay, so back to my question, GitOps or OperatorOps. When I titled this talk, I said from evolution from GitOps to OperatorOps, but I would strongly argue that it's not a binary choice. It's not that you have to do either GitOps or OperatorOps, but you can use OperatorOps for the magic that makes GitOps happen. So you can still have your declarative configuration in Git. You can just apply it to your cluster, and then you can have OperatorOps handle the remaining things out of it. But the biggest things that you get out of it are really the day two operations, which are very specific to whatever technology that you want to go. OperatorOps are also used in the reconciliation, or the idea behind that is used by crossplane.io and a whole bunch of other systems. So it's a very powerful tool. So the only really thing that I'm trying to sell you in this talk is the idea that please go and take OperatorOps or have a look at it. And with that, thank you so much. I'll take your questions, and we're always hiring. So